Hello, seekers. Welcome to the third video of the blockchain series. In the earlier video, we had refined the design of our solution and by introducing the idea of blockchain. Right? That was I think it was in the last video that we introduced the idea of blocks, wherein the entire ledger was divided into time slices, and we hashed that particular time slice into a block, and then we also refined that by chaining one block with the other, right? And that's how we landed on the idea of blockchain. And we also saw how that would significantly reduce the compute effort that is going to be required to do a checks and balance across nodes. However, that doesn't solve the problem of the amount of storage space that is going to be required by a node itself, which means by that device itself. So imagine that we are still looking at managing the entire ledger in every possible device, right? So that is a whole decentralized public ledger that we just went through. So which means that every node will have to hold all transactions of the ledger of every party, along with the hash values, of course. Now, which means that the device can easily run out of space, right? Especially when you're trying to hold transactions of for multiple years, it can easily it can easily go into gigabytes and even terabytes and petabytes, and it may not be it may not scale. So how do we optimize that part? So here is again we'll try to be a bit clever and introduce a feature here. So if you really see this, the block data, I'll tell you the significance of why this is colored red in a moment. But what we have seen so far is every node is going to manage a particular ledger, and these are the properties of that particular ledger. And based on certain time slices, blocks will be identified, and those will be hashed. Right. So this hash value is a hash of this block data plus the previous the hash value of the previous block's data. So that's what we've seen so far. Now, if you really see here, for A, the most recent transaction itself has the wallet value, right? So if you really see here, this is the moment when A gave $2,000 to B, which means that A's account wallet value has become $500 and B's wallet value has become $2,000. Now, if you really see the latest transaction value for A and B, it is these two. And if you really think this would suffice, right? The moment you have the most recent transaction, you don't really need the previous transactions at all. Because when you make this transaction, when you try to make a transaction with, let's say when A wants to make a transaction after this with the party C, C will just need to see what is the valid value of A, and that is present in this itself. It doesn't need all these values of all these transactions of A. So this gives you an opportunity to go ahead and remove the older transactions of a particular account, right? So for A and B, you don't need anything old. You just need to always have only the most recent transaction. Now, can you really do that? Yeah, you can do that, but there is only one problem, because if you try to reduce this, if you try to clear this whole thing off, then you really cannot recreate the hash value if you ever have to, because you've already created the hash value on top of the block's data, right? Because the block hash is actually built out of this block data plus the hash value of the previous block, right? So which means that the moment you get rid of this data, you really cannot recreate this hash if at all you ever have to, right? So how do we solve this problem? So now you think about it as and this data as two parts. Now this is the whole transaction data, and instead of having to build your hash value as a function of the block data plus the hash value of the previous block, what if you consider the hash value itself as a function of the hash of the transactions in the block data and the hash value of the previous block? So this is a change. So what this means is that you think about the construct of this block having two parts. Every block having the actual the payload of that particular block, which is the entire set of transactions, plus there is a header part of that particular block. Now that header part of that block is always going to have the hash of each of these transactions, and the actual payload will have the actual transactions. Now your block hash value is going to be the function of the hash of the transactions in that header plus the hash value of the previous block. Now with that design, you have decoupled the actual transactions value. You're free to now go ahead and clear off the transactions whenever we want if the size grows higher, and only retain the hash of these transactions in the header, right? So because the transaction of the size of the hash of a transaction is actually very small as compared to the actual transaction. So the way it would scale is much lower. And there is a nice math in the white paper of Satoshi Nakamoto where he says that even for years if you let that header grow, it will not go beyond a few gigabytes. So that is scalable. So the idea here is to evolve the hash value to be a function of the hash of the transactions in the block data, not really the block data, but the hash of the transactions and the hash value of the previous block. So that's a refinement that we'll bring in here. And with this refinement, we are okay to go ahead and clear off the actual transaction data as long as we retain the hash of those transactions in the header. So this will help us manage the storage space, and we can even take this further by not having to keep a block, keep even this data, keep even the block which includes even the hashed transactions for eternity. We can only maintain a rolling 5-year window or a 6-year window or whatever it be, so that you only hold the blocks for time slices in the last 5 years, and you can clear off all the blocks older than that. And because you are anyways having what this means is that you will really not go beyond 5 years to look up for any transactions. So obviously what this design would ensure that this design would entail a new requirement that everybody should make some transaction in 5 years. Right, if you choose 5 as a number, so that you have, remember, for you to transact, you need to have the most recent transaction in your blockchain. And if you're going to restrict your blockchain to be just 5 years, so you have to make at least one transaction so that your wallet value is available here. So that when you make a transaction, that lookup yields success. So this way we are able to manage the storage space. Now let us, So before we move on to the next thing, so the thing that we have introduced here is the idea of immutability. Why we say it immutable is because we have decoupled the actual transaction data from the hash values of these transactions, and you have actually we have now through our design we can actually clear off only the actual payload. Which means that the hash value cannot be recreated, right? The hash value of these transactions cannot be recreated. So, which means that these transactions that we make is immutable. You really cannot change it because the design allows you to delete them at any time. So, these are immutable transactions, and which makes the whole blockchain as an append-only system. You really cannot go back and change anything because the moment you add something to it, the transaction is actually hashed and kept, and that hash value is made use of in preparing the hash value of that block, and the whole chain is built on top of it. So the design doesn't allow any updates to it, and so your blockchain is actually immutable as well as it is only an append-only ledger. Right?
If you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.